Alright, hi everyone. Today you're going to be learning about molecular geometry. So in the previous class you should have learned how to draw Lewis diagrams. And now we're going to take those and turn that into an actual 3D structure and see how we can identify the shape from that 2D picture that you just drew. Okay? So getting started, there is a specific theory that allows us to make these predictions on what shape a molecule is going to take. And this is called VSEPR theory, VSEPR, which stands for valence shell electron pair repulsion theory. It's a long name, so we're just going to call it VSEPR theory. Essentially, it focuses on this: valence shell electron pairs, so the outermost electrons, and the fact that they repel each other. They want nothing to do with each other. They want to be as far away from each other as possible. So maybe it should be called the brother and sister repulsion theory. Maybe. I don't know. So here's what it really stands for. It essentially states that electron pairs within a molecule are going to orient themselves in order to minimize repulsive forces. So they're trying to get away from each other as far as possible. They're still going to have to be in the same molecule, but at least they're taking their space. Okay. So here's a picture to show you that if you had a central atom that was attached to two other things, those other atoms will be bonded essentially directly across from each other. This bonded pair of electrons can't get any further away from this bonded pair of electrons than it currently is. Okay. So what are we going to do? Essentially, we're going to look at how these bonded pairs orient themselves. There's two different kinds of bonded pairs of electrons, and they play different roles. So the first kind of pairs of electrons are bonding pairs. Okay. If I drew you a picture real quick to show you what this looks like, we have so if I have a nitrogen that's attached to three hydrogens, the Lewis diagram, if you went through the whole ordeal and drew things out, you would see that this is the Lewis diagram. Those are scary looking electrons. There we go. Okay. Bonding pairs would be these guys right here. This one, and this one. So there's three bonded pairs here. Very nice handwriting. Yep. You also have lone pairs. Lone pairs would be these guys. Okay. So lone pairs of electrons are not participating in any bonding. Both kinds of electrons take up space. Okay? They do have repulsive forces whether they are bonded or not. Here's the key thing though. Lone pairs are more strongly repulsive than non-bonding pairs. Okay? Or sorry, than bonding pairs. So these ones here are more repulsive. Way more repulsive. And so they're actually going to affect the bond angle more so than a bonded pair will be. Okay. So lone pairs can cause the bond angle between the atoms to reduce. I'm going to show you an example of how that happens. So I'm going to go back to my pretty little drawing app and show you two different molecules. So one example is, come on, go boron, go. It's hard to get the first atom on there. I don't know why. There we go. Got a boron. And three hydrogens. Okay, just going to clean this up really quick. And then another option, this first one is BH3. Well, NH3 has the same number of hydrogens, right? BH3 NH3. So the top one is the nitrogen with 3 hydrogens. The bottom one is a boron with 3 hydrogens. Well, if I rotate this, you're going to see that the BH3, the one in pink, is flat, totally flat. But the NH3 is not. And it's because there's a lone pair of electrons on that nitrogen. I just showed you the drawing, this Lewis structure of nitrogen, or of ammonia, and it had that lone pair up on the top. There's a lone pair on this nitrogen. There's no lone pairs on the boron. So that lone pair makes that bond angle squish down a little bit. So this bond angle between these 3 atoms here, that bond angle is much smaller than the bond angle here between the boron and the 2 hydrogens. Okay? So from this angle, they look pretty similar. But as you rotate them, if you start to rotate them, you see that they are definitely different. Okay? So we're going to look at how that happens. Alright, so how are we going to determine these shapes? How did I know that this is what it's supposed to look like? Well, it sure looked like I just hit clean up and hit geometry and it made it all pretty. Yeah, but I'm also expecting that you learn how to draw these structures in 3D and know where those atoms should be. Okay, so once again, I'm going to give you some lists of that you can follow to get these shapes. So, step number 1, when in doubt, draw it out. Draw the Lewis diagram. So you're going to use the rules that you learned in the last set of PowerPoints. You learn how to draw Lewis dot diagrams, Lewis dot structures. Okay. And then, once you have done all that, then you have to count up electron domains. So I'm going to switch back to this. And I kind of showed you how to do that over here, where we counted up electron domains around that ammonia molecule. We had the 3 bonded pairs and the 1 lone pair for a total of 4 pairs of electrons. Okay, so there's one lone pair, 3 bonded pairs, giving you 4 total pairs of electrons. Now, when you have double and triple bonds, those count as 1. Okay, so I'm going to show you an example. If I have the what's an easy one? Well, this one you'll probably see later, but this is carbon dioxide. There's 2 double bonds on that carbon. This is 1 lone pair, or 1 bonding domain, I should call it. And this is another bonding domain. So there's 2 total bonding domains. Okay? 0 lone pairs. So anytime there's a double and a triple bond, count it as 1 domain total. And it's a bonded domain. Alright, and then the shape is going to be determined by the number of those domains. And you're going to need to know 8 common shapes and their bond angles. This is going to be something you have to learn. You won't be able to use the graphic organizer that you're about to make on your final exam. I will probably let you use it on your unit exam, but that's it. I can't allow it on the final. Okay, so you do need to start learning these shapes, and what better way to learn them than practicing. Okay, so find this paper in your homework packet. You'll see it's right after the Lewis dot diagrams and right before molecular geometry. So this chart, we're going to go through all 8 of these structures. You're going to be filling in the number of bonding domains, the number of non-bonding domains, the total number of domains. We are going to skip hybrid for now. Skip for now. Okay? Skip for now. Do not cross it off. Don't pretend like we won't come back to it. We will. Okay? you're going to want to draw a picture, and you're going to need to draw it in 3D. So I'll try and show you using the iPad as best I can how to draw some of those 3D shapes, okay, onto your chart. You're also going to need to document the bond angle and write down what an example molecule is. Okay? Are you ready? You can always pause the video. All right. So the first one is called AB2. Okay? So AB2 has 2 bonding domains and 2 lone pairs for a total of 2 domains. Okay? And its shape is called linear. If it's linear, what do you suppose the bond angle is? It's a line. It's 180 degrees. Okay? The shape is like this down here. Pretty easy to draw out. An example is BeH2. To prove that I'm not lying to you, I'm going to draw this. Here we have a table, beryllium. Come on, beryllium. There we go. Beryllium and 2 hydrogens. Clean it up, and now you see it is totally linear. It's flat, has a bond angle of 180. Beautiful. How do I know that that's the case? Beryllium has 4 electrons. Just kidding, it has 2. Hydrogen has 2 electrons. Oh my goodness. For a total of 4 electrons. Beryllium's in the center. Hydrogens are each out to the side. So that's how I draw my linear shapes, just like that. Okay? All right, next one is AB3. This one has 3 bonding domains, 0 lone pairs, 3 plus 0 is 3 total domains. It looks kind of like looks kind of flat, right? So this is one that we showed a little bit ago. It is totally flat. You can see that right here. It is very symmetric, so I could rotate this molecule. And you might not notice, except I'm zooming in on accident as well. Okay. This is called trigonal planar. Since it is exactly, it's perfectly symmetric, each section is equivalent. If you take a circle and divide it into 3 equal pieces, what bond angle should you have? That's right, 120. An example molecule is BF3. So this, what I've just shown you, is BF3. Okay. All right, next one is called AB4. It has 4 bonding domains, 0 lone pairs, 4 total domains. This is where things get a little bit messy. So if I put a new page here, I don't know why the first atom is so hard to get in there. There we go. We got a carbon, put 4 hydrogens in. Now this currently looks like a hot mess. Wow! There we go. Okay, never mind. We'll clean it up. And now when I rotate it, you'll see that it is actually incredibly symmetric. Okay? This is as far away as those bonds can get. It's no longer flat. It's taking on a 3D shape. This is what makes carbon so magical, is this shape right here. Okay? It is called tetrahedral. It means 4 faces. I don't know if I can show that on my iPad. I don't really know how. Okay. But if you consider that each of these triangles essentially makes a face, and as you rotate, there's another face, there's another one, and there's another one. Okay? So 4 faces. The bond angle is a little messier, but it's 109.5. The example is CH4, methane. All right, next one, AB3E. This is where things start getting messy. This is where we start needing to have, here's an example of AB3E. This is where we start having lone pairs hanging out on our structures. And that's what this means, AB3, three things bonded, and then one electron pair. Okay? This one is trigonal pyramidal. I showed you this structure a second ago. I'll erase the new sheet here. Get our nitrogen down. Come on, little guy. There's nitrogen. 3 hydrogens. If I clean this up, notice it's not flat. It doesn't look like it has anything above it, but that's where that lone pair is sitting. Okay? That lone pair causes those bonds to squish down away from it. And so it looks like a pyramid. Okay? And it has a triangular base. The bond angle for this guy is 107 degrees. And our poster child, AB3E, is ammonia. Okay? Lone pair hanging out on the top. And we saw that here. And so this lone pair up here, this is the thing that's causing that structure to be squished down and not flat anymore. All right, next one, AB2E2. All right, now this is also AB2E. It's kind of messy because it has 2 possibilities. Okay, so I'm going to first look at AB2E2. AB2E2. This is when the central atom has 2 lone pairs on it. Okay. Our example is water. It has 2 lone pairs. Okay. If I draw this structure, oxygen, 2 hydrogens, clean it up, show the actual geometry, is in fact bent. Okay. Which is the name of the structure. So it has a bond angle of 104.5 for this one. Okay. So 2 bonded, 2 lone pairs, 4 total, and this is 104.5 degrees. Looks like 104.6. Come on. All right. AB2E is also bent. But in this case, it only has 1 lone pair. Okay? And it has that 120 bond angle. Less than 120 degree bond angle. Okay? Why is that? Well, there's 2 possibilities. There's the AB2E2, and then there's the AB2E. They're both bent. Okay? And it has to do with how many lone pairs it has. So the AB2E2 has 2 lone pairs. The AB2E has 1 lone pair. Okay? Bond angles are not the same. You'll see that these are just slightly smaller than if instead of having the E, it was a bonded pair. Okay? So if it was AB3, that bond angle was 120 degrees. Switch it out for just an electron pair, and you get less than 120 degrees. For AB2E2, this would have been tetrahedral if it was AB4, and it would have been 109.5, but switch out 2 of those bonds for 2 electron pairs, and you get just less than that. Okay. So our poster child for bent is the water molecule. All right, keep on going. Our next one is AB4E2. I'll draw this little friend out. I'm going to make a nickel center. I'm going to put some carbons up. Oh, come on. I don't know how it's doing that. Eee! There it is. Okay, carbon. And then we're going to put some nitrogens on it. Like little arms and legs. I'm going to clean this up. I'm going to do it again. I know it's kind of messy. Oh, fuddy dud. That's not what it's supposed to be. Did it earlier. Did not work. Hold on. Another example would be. I'm doing really good today, aren't I? Imagine if I was in person. Yeah. There we go. There we go. This molecule is called, well, let's see if you can guess. It makes this shape. This is a square, and it is flat, so it is called square planar. What bond angle does it have? Hopefully, it would stop drawing random elements. The bond angle, since it's a square, should be 90 degrees. Okay. So the structure I was trying to draw out for you earlier, and tried to make it a tetrahedral, is nickel tetracyanide, and it's actually a polyatomic. It's a complex ion, so we'll not mess around with this a whole lot. But I was going to show you how to draw some of these in 3D as well. Maybe I'll save that for the end. I'm already on a roll here. Okay, so I'll show you how to draw the 3D structures in a second. All right, we're almost there. We have AB5. So for this one, I'll take a phosphorus and we'll put some chlorines around it. I promise I practiced this before I did this. Clearly not enough, right? Put some chlorines on. 3, 4, 5. I'm going to clean up. I'm going to do it again. And now we have this very beautiful molecule. I like to call this my ballerina molecule because you can make it dance. Okay. It is very symmetric. You'll see that there are 3 atoms around the center. And they look almost like they should be in trigonal planar. So there's my trigonal plane, okay? And then the other 2 atoms are above and below. So there's 5 total domains, no lone pairs on this one. This one's called trigonal bipyramidal. It's like you've got 2 pyramids base to base. You can visualize that. Okay? The bond angles, there's 2 of them. So I'm going to show you the first one. The bond angle from here to here is 180 degrees. If I rotate the molecule, the bond angle from here to here is how much? It's 120. So 2 angles, both required. Okay? Our example molecule is PCl5, is what I drew. All right, last one is called octahedral. This one has 8 faces, octahedral. Okay? Though it has 6 things attached. So an example, we'll take our sulfur, We're going to put fluorines around it. Get back here. There we go. I'm going to clean this up a little bit. It seems to have trouble cleaning it up correctly on the first try, but there we go. So this one is also incredibly symmetric. You see that it is, there's the two that are like the head and the foot. They're like a jack, if you ever played that game. And then you rotate the molecule just a little bit, and you can see it kind of looks like square planar. So it's square planar with the atoms attached to the top and the bottom, or above and below. Okay. So what bond angle does this look like? Well, that looks like 90 degrees. If I rotate the molecule a little bit, that looks like 90 degrees. Rotate it again. That all looks like 90 degrees. So all the bond angles are 90 degrees on this one. Okay. And SF6 is our structure, or is our example. Okay, so let me show you a little bit how to draw the 3D structures for some of these. So, this bigger screen. All right. So for linear, pretty much just that, right? Trigonal planar. We've got three things attached to our central atom. Tetrahedral is where it gets exciting. Okay, so I'm going to try and draw things really nicely. So here's my central atom. I'm going to have one above, one off to the side. I'm going to use hashed bonds to show the bonds going back. And I'm going to use wedge bonds for the atom coming out. Okay, so that's a 3D showing of our tetrahedral. It's very similar for drawing trigonal pyramidal, except this time you leave a lone pair up at the top. So wedge bond outward, hash bond back, and then lone pair. Sometimes it's really fun to make it like a little ghost. After trigonal pyramidal, we had bent, I think. So bent, we've probably drawn water before, just like that. You can put two little ghosts. The other option of bent is this. So this is A, B2, E2, and this is A, B2, E. Okay. After bent, maybe we have square planar. Square planar. So here's my central atom. Hashed bonds to the back. Wedged bonds outward. Got lone pair above. Lone pair below. Make some ghosts. Beautiful. And then we had trigonal bipyramidal. Running out of room. How about I go to the next slide? Is this above, below? So there's the head and the feet. We have hashed bonds back, wedged bonds out, and one to the left. So it dances as it spins. Octahedral. Here's the central atom. Above, below. Now very similar to square planar. and boom. Okay, so those are how you draw out those structures in 3D. So here's that one, and there's that one. Go ahead and pause the video, move back and forth as you see what's necessary. Okay? Alright, so let's do some quick practice. PF3 is our first practice problem. Remember, the first thing to do is draw it out. So PF3, phosphorus has 5 valence, fluorine has 7. There's 3 of them, so that's 21. Total, 26 electrons. Who's the monkey in the middle? Phosphorus. So then I throw in my phosphorus, or my fluorines around it. I use 6 electrons, I got 20 left. So I place in electrons all around. I put in 6 electrons for each fluorine. That means I use 18, there's 2 left. Where do they go? And the only other place is on the central atom. I'm making them very bold here. Okay? So all I have to do now is count up my domains. I see that there's 1, 2, 3 bonding domains. And I have 1 non-bonding. Okay? If I look on my chart for the 3 bonding, 1 non-bonding, total of 4 domains, I see that it should be what? Look on your chart. What shape should it be? Dun, dun, dun. Did you say trigonal pyramidal? I hope so. What bond angle would that one have? 107 degrees. Okay, so that's what you would have to do with this sort of structure. And it looks like this. It is squished down a little bit. It is not flat. It has that lone pair up on the top of the phosphorus. It looks a lot like ammonia. Alright, CO2, of course my animation already showed you what the structure is, but carbon is 4 electrons, oxygen is 6 times 2 is 12, so a total of 16 electrons. If I put my carbon in the middle and my 2 oxygens around it, I use 4, so I've got 12 left. Place them in all around. But I don't have enough to put anything else on carbon. And carbon needs an octet. So we take 2 of those electrons from the oxygen and make it a bond. Take another set of electrons and make it a bond. So now I have this structure with 2 double bonds. Well, if you remember, when we're counting up domains, I am counting up bonding domains. All the time they're going to be counted up as 1 domain. So there should be 2 bonded domains in this structure. If there's 2 bonding domains and no other domains total, it has to be what shape? That's right, linear. Linear has what bond angle? 180 degrees. And it looks like that. Okay. You made it. You now know how to do molecular geometry of molecules. All you need to do first, draw out those Lewis diagrams, count up domains, match it to the shapes on your chart. I will admit that there may be 1 or 2 molecules in your homework, in the next 2 homeworks, that are not they're not one of your 8 shapes. It's because you did not learn all of the shapes. There are also this thing called T-shaped, which looks like this. And it has, I think, 2 lone pairs. And then also seesaw. But I think those are cute names for molecules. They're all derivatives of the trigonal bipyramidal. This one has one lone pair. So these two possibilities are also in there, but I'm not asking you to memorize them so that you might see them on your homework. I apologize. It's too late now, though. So your homework is this molecular geometry worksheet. It's actually not called the practice one. So find the one that is the first molecular geometry worksheet. There's two sides. All you're doing is drawing Lewis diagrams, counting up bonding domains and non-bonding domains, and identifying shapes and angles. Okay? So that is the limits of the homework for today. If you need extra help, there are bajillions of resources out there. I have selected 2 and posted them on our class website as extra help. Okay? Once again, if you have trouble, take a picture of what you've tried, send it to me. I will help, troubleshoot.